thing. The meaning of this LVW, this as a vector space. That's the first thing I'd like to talk about. We recognize this as a vector space. First, this as a subspace of all functions from V to W. Not linear map. Think about all the functions from vector space V to vector space W as sets, right? Okay, level of sets. And we know space of functions make a vector space, right? Especially here, it's a bit more involved that V has, what does that have? I think it's a matter of what this, so if you recognize all functions as a vector space, I'm going to call that vector space big C here, curly C. This is a vector space. It comes with a scalar, right? It's over what scalar field? That's a trick question. V already has a vector space scalar field over there in the V, right? W as a vector space, it comes with a scalar field. Which scalar field inherits these? Which scalar field this space of all function inherits in here? Is it going to use this space field, this scalar field, or that scalar field? I was misspeaking. This has its own scalar field, right? Right. What about this one here? It has its own scalar field. As a function, it doesn't matter, right? You can have a Q, you can have something finite field. That is not a problem in terms of just being functions. So if you recognize the space of functions from V to W as sets, which scalar field is going to use it? It's going to use the scalar field of V, or it's going to use the scalar field of W? It's a good question. All right, let's say we have S and T. These are two functions, right? Not linear. Functions from V to W. So we obviously have sum. There's no problem. You can add two functions. Input value will be sum of the, output value is the sum of the two outputs of this individually. So sum is all right, and everything else is all right. It is just that we are about to define A times S, right? We're back into this C. That's what we have to give a meaning to. We're going to multiply a scalar to this function and still inside the C, right? If you think about the meaning of AS, S is not a number, so you have to give a meaning to this AS, right? How do you give a meaning to a function? It's showing that where the input goes, right? If I'm giving the input, what is your definition of this thing? Is it A times SV, right? SV here. SV is functions from V to W, so that must be a vector in W. Do you agree? This is a little v. So if you want to multiply something to W, only thing that's given is a scalar field of a W. So that's right. This one nicely inherits a scalar field of W as a vector space. Correct? There's no linear. If you just look at a space of vector function, and that's what the scalar field inherits. Now this one is a subspace. That's how we recognize it, right? So if this is a subspace, all you have to check is three things. If the 0 is there, if the sum is closed under the sum, closed under scalar multiplication, right? And then it becomes a vector space. So the point is that you don't have to check all those axioms, just the three things, if we first recognize this as a subset of vector space, the bigger vector space we're sitting inside, right? Remember this one, what additional property does this one require? Not just all function, right? What kind of function? Linear map, right? Correct? Linear map has this property. If it is T is a linear map and applying AV, then A go outside and V like that, right? Remember that? So A is a scalar field of vector field V, and A is also a scalar field of a vector space W, right? So they have to be the same. If this one makes sense at all, right? So I didn't even emphasize it here before. If we're considering linear map from a vector space V to vector space W, we are assuming that their scalar fields is the same. Okay? So that's the linear map. So we also consider this null space of T. Remember what that is? That's a subspace, right? And this is also a general name, and you see this name more in advanced mathematics textbook. Kernel of T is the same thing, slightly more general idea. Null space T, kernel of T is the same thing. And we have range of T, correct? That's a subspace. This null space of T is a subspace of what? V or W? How about the other one? Subspace W goes inside. And this one is also denoted by image of T. Right? That's the general name for that. And if it is all finite dimensional case, the dimension of, since it's a subspace, we can certainly think about dimension of range of T, right? Okay, dimension of null space of T, dimension of range of T. And that one is called rank. Okay, you might have heard that term in the first year course. So here's one example I'd like to go through. All right, I have one vector space, V, that is spanned by some 5 vectors, just like that in the example, and dimension of V is 5. What does that V1 through V5 make? It's a basis, right? It's a full dimension. There's no repeat on that. So here's my T1. T1 is sending this VK. This is what I expected in that homework. Exactly to VK, right? Does definition of T1 make sense? Sending V1 to V1, V to the V5. What about all the other infinitely many elements? It is determined. Remember that part? If you know where it sends to base members, everything is determined. So it is sufficient to define it like this, and you know what happened to the other part. And there is no matrix here, right? These are not column vectors. So this is in general how it's described. I'm going to do T2, that VK is going to go to VK plus VK plus 1. That only makes sense if K is less than or equal to 4, right? Because we reached the 5 in there. So if it is a 5, if K is 5, I'm just going to go V5 and go around to the loop. Is that all right? How about T3? And T3, I'm going to go similar thing, but this time VK minus VK plus 1 if K is less than or equal to 4. And if K is 5, I'm going to do the similar thing, just opposite sign. So I have 3 linear map. Let me ask a silly question. Why is this T1, T2, T3 is linear? Why is T3 to T2 linear? It's only defined over the base element and expanded so that it's linear, right? I didn't give a definition for all the elements. I only give a definition for the basis element and then extend it so that it becomes linear. Right? But it still asks the question, what about in between this relation between this V1 through V5? There's something I have to think about. But I claim if you just define it arbitrarily, V1 goes to whatever, that always defines a linear map. All right, just like that in the homework problem. All right, the question is that if you recognize this T1, T2, T3 inside where? Inside some vector space, right? Okay, so what is the T1, T2, T3 sitting inside? What kind of vector space in here? This is a linear map, right? From where? V to... Yeah, there are VKs go to VK. That's same world, right? VV, and these all things are VV. So we recognize this one in here. T1, T2, T3 is inside LVV. This was a set before. Now this is a vector space. Is that right? Correct? The linear map from V to B has a special name. It's called endomorphism. Fancy name in the algebra. Endomorphism. Going V to V self, the structured space. If it is V to W, and it is L V to W, there's no short name. For endomorphism, V to V, we have a special name. Next thing is that if you have three vectors, is what is the usual question we ask? Linearly independent. That seems like a next question. So, linearly independent or not? That's the question I'd like to ask. Okay? So how does that go? I give you P1, P2, P3, and I ask you linearly independent. What is the question? You write it down. What is the equation there? You write it down. Let what to be 0, right? Something to be 0. What is it? Scalar A1 times T1. T1 is not a vector. It's not a vector V. It is the function, right? And multiplied by A1. A2, T2, A3, T3. Right? Now how do you understand this 0 here? What is 0 here? It's a 0 vector, but it's a 0 function, right? 0 function from sending V to V, right? This function sends everything down to what element? 0. V1 goes to 0, V2 goes to 0, V3 goes to 0, V4 goes to 0, V5 goes to 0. That's this map here. And once you set up like this, we want to show whether A1, A2, A3 are equal to 0, right? That's the question. Correct? Then what do we do? For the function, we just have to plug in the values until we get our hands on to the A1 and A2, A3. Okay? So, what are we going to do? A T1, V1, right? And a T2, what are we plugging in here? V2 or V3? So this is a function. You recognize the left-hand side as a function? We're plugging in one vector there and set it equal to 0 and see what we get. So what are we plugging in here? V1, thank you. And what about here? A3? T3 V1, right? And it's supposed to be 0. So what do we know about this one? It's a V1. The first function doesn't do anything. V1, V2, V1, V1, V2, V2, right? So that's V1. What about second one? I think it was a V1 plus V2, right? Plus V2. V1 goes there and plus V2. How about the third one? V1 minus V2, right? That one is exactly the same index, minus 2. That is equal to 0 now. Okay? So can you rewrite this one? If it is like that, what would you do? A's are scalar and V's are the vectors in the domain. So we're going to collect all the V1s. A1, A2, A3. Those are the collection of V1, right? I see it here. I see it there. Correct? How about V2? What do you see in the V2? A2 minus A3. Is that right? You see that? Okay. Is that equal to 0? That's all that vectors involved, V1 and V2. There's no V3 or higher involved, right? Okay. So what can you say about from here? V1 and V2, they are linearly independent. Why is that? because v1 through v5 is linearly independent. Any subset will be linearly independent. So what conclusion do we have? A1, A2, A3 is 0. What about next one? A2 minus A3 is 0, right? So does that imply that A1, A2, A3 are all 0? You can stick A3, 1 here and come up with all the other combination. You see the one free variable? So we failed to show A1, A2, A3 is 0, right? But is there a way to go for more? Well, we just stick in V1, right? Why not V2? All right? So I stick in V1 and I got this one. What if I stick in V2 here? It's supposed to be 0 as well, right? So can you go ahead and do that and get this type of equation? And then it might be a slightly different equation, right? And hope that gives you a third equation. Boom, that goes you the 0 there. All right? So why don't we work on that? Just 1 minute or two. Just try this exact same idea to come up with this nice equation about A1, A2, A3 that we want to solve, right? We want to conclude these are the zeros. You get exactly the same thing, right? And you understand why. Hopefully, it's shifting, it's kind of giving you exactly the same relationship, it seems like. You agree? So, I bet it's going to go all the way up to V4. V5 is like that, right? I bet this is exactly the same. So what is the next thing you want to try? We didn't get any new relationship in here. I think I'm definitely going to try V5, right? That loop around a little bit different, seems to me. I'm not going to try 3 and 4. Seems like that's going to be exactly the same equation. You can try. All right? Let's try V5 then and see if you get something different. So I'm not showing the V5 in here. V5, go from V5 to V1, loop around, and a different sign. See if that's different. Is that same? I think we get exactly the same thing, right? V5 and V1, we have A2 minus A3 is V1 equals 0, right? So by trying all this V1 through V5, and this is the only relationship we get, and we fail to still conclude that A1, A2, A3 is necessarily 0, right? That doesn't complete the proof of its dependency, right? The best way to conclude from here the dependency is that let's find, so from all that we get this same equation, nothing further. So let's find one example, right? So what do you see in one example? A3 being 1, right? What about A2? By looking at the third equation, A2 must be 1, right? What about A1? Here 1, 1 is a negative 2. Right? So it seems like this combination actually make this function 0. And you have to just show that. Final step. So final step, and show negative 2 times the t1 plus t2 plus t3 is going to be 0 function, right? How do you show this is 0 function? You plug in v1, you plug in v2, all v5, and they're all 0. Then it determines it to be 0, right? But that calculation is kind of repeat of this one. But logically, you have to state this one. And if you set it like this above calculation shows that is actually 0. You don't have to repeat this one again, but that logic better be there. Right? You failed to find A0, 1, and 2, 3 being not necessarily 0 doesn't prove that it's dependent. And to dependence is to clarify that this combination is actually 0 function and the coefficients are not non-zero, therefore is dependent. Okay? That logical structure is important, then you repeat all this calculation. If I just ask you to, this is dependent, just prove it, then you will just fish around this coefficient and discover one or another. But if you don't know whether it's dependent or independent, wouldn't you go through this process until you discover this lockdown of this A2, A1, A3 being completely zero, and you conclude dependent? You failed, and you kind of wrap up your argument nicely that it's actually dependent. That part is actually dependent. You have to argue or elaborate. Does this example make sense? Yeah, so example, I went through it like this to for us to feel a little bit better about this LVV as a vector space and its linear dependency. Question. Okay? One of the homework problem was finding these elements T1 through TL, right? And showing it spans, correct? Showing that spans, that's one of our questions. What is the next level of question? That part B was missing, right? That also only had a part A in the homework. The part B was actually asking, this is actually find a basis. Not just the finitely many that span, but find the basis. Additional argument is that the thing that you have to go through, the one that you have is actually linearly independent, right? Linearly independent. And how are we going to show this is linearly independent? This is the naive approach. But if it is general, if this is one algorithm, all right? And you don't know at this stage from the definition how many V1 VKs you should try to get something. If very unlucky that all the way down to 5 you didn't get anything new. Therefore, you have to wrap up. Okay, that's we want to conclude it's dependent. Maybe in some example with the 1 and 2, V1 and V2 gives you 3 different equations, right? And that gives you trivial solution, and then you conclude this is deep independent, right? Things like that. So if you happen to have one more condition, A1 through A2 minus A3 being 0, these 3 things together will conclude A1, A2, A3 all should be necessarily 0, therefore independent. Make sense? So these are linear maps, and span you thought about a little bit in the homework, and these are the discussion of linearly independent of linear maps. Okay? It is a permutation. T1 is a V1, the same thing. T2 is ascending V1 to V2, V2 to V3, and T3 is a V1 to V3, V2 to V4, skipping 2 indices, and those are good examples of independent. And then if you try that, you're going to easily, I'm going to make that as a lecture review problem and show that as independent. All right? You're feeling better about independency of linear maps? All right. This is I think the gist of this advanced linear algebra. They want you to look at the vector spaces. On top of it, there's another vector spaces, right? I see a vector space here, V, right? What is the vector space on top of this vector space I'm talking about? LVV, right? So I started with this V, right? There's a vector space. Nothing else. But you can just out of nowhere create another vector space. What is it? Endomorphism, the V. The linear maps going from V to V. Isn't that another vector space, right? Right. So that's it's a good idea in many applications to look at, to distinguish this. If V and W, they look quite the same, and how can you distinguish it? If their endomorphism is different, then you can conclude that they are different animal. Things like that. But it's something that they do a lot in this advanced linear algebra. Abstract vector spaces. Let's go a bit further with these examples. How about this example here? V being this thing. Who remembers this one? Curly PR. polynomials all with the real coefficients, right? So let's think about endomorphism V. All the linear map that sends a polynomial to polynomial, right? All right. How about the dimension of V? Remember the dimension of V? 90-degree rotation of dimension 8. All right? Yeah, 90-degree rotation of dimension 8 is infinity. So it's a dimension infinity, and we're considering some maps in a T1 is a ddx. Does it look like a map? If I give you a polynomial, you hit it with a ddx, and you get another polynomial, right? So that's a function from B to V. Why is this linear? Students usually spend 1/4 of this, or probably the eighth of a calculus 1 student spend the sum rule and difference rule. Remember those? Let me write it down. Sum rule says if you have sum of two functions, differentiate is the same thing as you differentiate individual functions and add it later. Different order of operation, right? Add first, differentiate later versus differentiate first and add later. Different order of operation is now a fancy term. What is that? Linear. This thing, the operation we're doing, is actually a linear operator, right? What is a scalar here? Scalar multiplied to a function, right? What happened to that scalar? Goes outside. That thing you already knew is really the linearity of the operation business, right? So this operator is a linear operator. Okay. How about second derivative? Do you think that's still linear? All the higher order derivatives still linear. So here's another interesting map, T2. It's kind of difficult to write down. So it's a 0 to x integral and blah and dt. What that means is that if I give you a polynomial here, and you stick that polynomial in t here, and integrate and evaluate at 0 and x, you believe that's another polynomial? If you integrate polynomial, it remains a polynomial, right? Therefore, you're calling it inside. So that defines a map from B to V, don't you think? If I give you a polynomial, integrate. So for example, I give a polynomial T2 of what polynomial do you come to your mind? X squared minus x? X squared minus x, right? What we do is that you put the 0x and change that to t. Now you integrate with respect to t, which is 1/3 t cubed, right? Minus 1/2 t squared, and plug in 0 and x. Then it becomes a polynomial, correct? But is this linear? You have to think about it. Maybe you actually have to prove it, right? And using some of the theorems from calculus. You can integrate later and add first, all that. Again, fancy name for that property is a linear. It's the prevailing property of the linearity in the theory of a whole calculus subject, if you look over, and that everything is called linearity. All right, how about this T3, which is x squared times f? You better write it in this way. If I give you a polynomial f, and you multiply x squared in there. So, for example, if I give you x squared minus x, T3, what is the map? You multiply x squared, so it's x to the 4th minus x to the 3rd. You see that? That's a polynomial. Why is this linear? It is actually linear. All right? T4 is a little bit of convoluted, just like that Laplace transform kind of flavor in it here. F is a polynomial, and this is what I'm going to do. The main variable x is actually postponed to the outside like this, x like that. And it's not just ft, this already we did it here, but x is somewhat involved in here, like x minus t, dt. Okay? Now while you're integrating this inside, with respect to t, we treat x as a constant. Is that okay? Then once you integrate it, plug in 0 and x. So here's an example. T4 of x squared minus x squared minus x. So like that. What you do is 0 to x, right? Now, what is f of x here is x squared minus x. Instead of x, you're going to plug in x minus t. So it's x minus t squared minus x minus t. Right? You repeat this polynomial x minus t inside this integral, but x is replaced by x minus t and x minus t. You see that? Now, when you integrate this one, you treat x as a relative constant. Okay? Then you first, however you do it. And I hope you see now this is going back to a polynomial in x. Is that right? Okay, that certainly defines a map from polynomial to polynomial. Why is this linear? You know, all that is something to think about. And once you do that, what is the next thing we do? Can I compute the kernel? Can I compute the range? Can I find the basis of a range? And then can I find those things? I believe with this definition, you can definitely go through. And at last, these T1, T2, T3, T4 are linearly independent. Right? And those things that I'm going to challenge you.